Alright, so what we're going to be doing in this video is mostly continuing some review of some basic concepts that you already know. First off, we're going to be dealing with exponents, the different rules and how procedures to work with them. Some simple scientific notation, nothing really hard. And then finally, roots and radicals, and that might sound unfamiliar to you, but when you see it, you're like, oh yeah, I remember that when I was in high school. So first off, I want to start with exponents. Oftentimes in mathematics, we take a number and we multiply it by itself, or we take a variable and we multiply it by itself several times, such as 2 times 2 times 2, or a times a times a times a. However, this is annoying to write and annoying to say, and so we shorthand this by using laws of exponents, rules of exponents. And the way we generally write exponents is this. A, and then there's this superscript that we call n. All right? This seems probably familiar to you, and it should. This A is what we call our base. And the n is what we are calling the actual exponent. Now, what does this mean? All right. Well, the base is what we're multiplying constantly. Okay. So if I were to say 2 times 2 times 2, well, the number that I'm constantly multiplying is the number 2. So I would say 2. All right. That's where my A would go. And the exponent represents how many times I'm multiplying it. So in this particular case, I'm multiplying 2 3 times. So my n is going to be 3. All right, this is how we basically write it. So 2 times 2 times 2 is 2 superscript 3. However, we don't normally read it that way. More commonly enough, this is how we really read things. So when I were to go to read this, I could say a raised to the nth power. That's one way I could say it. Or I could say the nth power of A. So going back to our original statement a while ago, we had 2 superscript 3. This is more commonly, as Ray said, 2 raised to the 3rd power. Or it is the 3rd power of 2. So if I have some other numbers, I could say A and 18. This is really A raised to the 18th power, or it's the 18th power of A. Okay? These are basically how we read it. So just to kind of give you another little example, and then we'll move on. If I did this, B times B times B times B times B times B. Well, the number I'm multiplying constantly is B, which is here. And I multiply it by 1, 2, 3, 4, 5, 6 times. So I am saying B raised to the 6th power, or the 6th power of B. When working with exponents, there are some rules that we generally follow, especially when we're multiplying exponents, dividing exponents, raising exponents to a power, and all these other little things. So what we're going to go now is over the basic rules dealing with exponents. I would suggest that we're going to go through these quickly. I want you to, in your notes, make sure you write those rules down. They're going to be using them as a guideline to help you with further problems. Your rules are going to be right here. So our first rule that we're going to be talking about is called zero exponent rule. Okay? So if I take a number and I raise it to the 0 power, it's always going to be equal to 1. It does not matter what that number is. If I have 8 raised to the 0 power, it will equal 1 automatically. No math involved. Just memorize it, right? No math. If I have 18 to the 0 power, it is raised to 1. If I have negative 18, notice how I put this in parentheses. We'll talk about that maybe a little bit later in class. But negative 18 raised to the 0 power is 1. So the zero exponent rule, just that simple. Any number raised to the 0 power will always be equal to 1. So now let's talk about the next one. This one's called what we call the product rule. Well, the product rule, it looks like somebody took TNT and stuck it to the alphabet and it just explodes up. However, let's do some numbers and it's a whole lot easier to understand. You see that in the rules here, it says a to the m power plus a to the n power is a to the m plus n power. What in the world does that mean? Well, let's do some numbers. Let's do it simple. 2 to the 3rd power times 2 to the 4th power. Well, notice, what do these both have in common? They have the same base, and in this case, it's 2. All right? So, we write it down. It's 2. But we got to figure out the exponent. Well, according to our little formula that we have over here, our little rule, is telling us to take these two exponents, 3 and 4, and add them together. Well, what's 3 plus 4? 7. So, what we have just discovered is that 2 to the 3rd times 2 to the 4th is equal to 2 to the 7. And, all right, so you might be asking me, prove this to me. I don't believe you. All right, I'll prove it to you. 2 to the 3rd is 2 times 2 times 2, right? So, and it's telling me to multiply it by 2 to the 4th. So I'm going to say times, I'm going to do 2 times 2 times 2 times 2. Well, that's my 2 to the 3rd here. Here's my 2 to the 4th. And when I multiply it all the way out, my base is still 2. But how many times am I multiplying 2 by? 1, 2, 3, 4, 5, 6, 7. So my answer is still 2 to the 7th. It's a whole lot easier just to follow the product rule than to try to work it all the way out like this. So, one more problem with you. If I have 3 to the negative 6, and I'm going to multiply that by 3 to the 7th, okay? Oh my Lord, well help us. We have a negative in here. It's okay. The rules still apply. What's the common base? 3. All right? So because I'm still following the product rule, I'm going to add negative 6 plus 7. Well, negative 6 plus 7 is 1. So our answer for this is 3 to the 1 power. However, here's another little rule. Any number raised to the 1 power will equal itself. So 3 to the 1 is just 3. Last one. Same rules apply, product rule. We're multiplying. We know the base to be 3. We know we're going to take negative 5 and we're going to add it to 5. So when we do, we get 3 to the 0. Uh-oh, that looks very familiar to our 0 exponents. So 3 to the 0 is equal to what? 1. Our next major rule is called the quotient rule, which is right here. Okay? Again, it looks complicated, but it's really not that bad. Where in the product rule, we added the exponents. In the quotient rule, since we're now dividing, we're going to do the opposite of multiplication. If we added in multiplication, we simply are going to do what? Subtract. Okay? So, if I have this, 2 to the 6, divide by 2 to the 4th. Well, are my bases here the same? Yes, this is the same and this is the same. So, 2. Well, since I'm dividing, I'm simply going to subtract my exponents. 6 minus 4 gives me 2. That's it. That's all you got to do. We could prove this and rewrite it to say 2 times 2 times 2 times 2 times 2, 1, 2, 3, 4, 5, 6 divide by 2 times 2 times 2 times 2. When we do this, we would see that these 2's cancel out. This one cancels to this one, this one, and this one, this one, and this one, this one, and this one. What's left? Just these guys, which happens to be 2 to the second power. Let's do a few more. All right, let's say I have r to the 9th divided by r to the 8th. Okay, well, my bases are the same, so r, easy. 9 minus 8 is 1. Well, like I told you earlier, any number raised to the 1 power, we could just simply say this is r. Here's another one. R to the 6th divided by r to the 9th. My bases are r. I'm going to subtract 6 minus 9. Well, 6 minus 9 gives us r to the negative 3. Okay. Now, this is okay. You are going to come up with exponents that have a negative in it. We will be doing some more things dealing with negative exponents, but not right at this moment. One last one. Let's do 8 to the 4th, divide by 8 to the 2nd, divide by, oh no, we're throwing 3 in there, 8 to the 2nd. All right. Just because I have 3 operations happening here doesn't change anything, okay? What do we notice? All of them have the same base. So it's 8. Well, what's my exponents? I have a 4 minus 2, because I'm dividing, minus the other 2, because I'm dividing. And when I get that, I'm going to get 8 to the 0. So ultimately, this is equal to 1. All right. Now, hopefully you've been catching on to something I've been saying. I've been telling you because the bases are the same. I want to show you this, and then we're going to move on. If I have this, say r to the 3rd times n to the 3rd, I cannot combine my exponents for the simple reason r and n are not the same base. That's something you might want to remember, so be very cautious on that. So the next rule that we're going to talk about is the power of a power rule, where in previous ones we were either adding or subtracting the exponents. This time we're simply going to multiply. So let's do a really simple one. Let's just say 2 to the 2nd power raised to the 2nd power. Well, in this case, all we're really saying is that the base is still 2. Here is my base. It is 2. And I am going to take my power, which is 2 here, and I'm going to multiply it by this 2. So ultimately, I'm going to get 2 to the 4th power. So really, what just happened? I took this exponent and I multiplied it by this exponent. This only works when we're raising exponents by an exponent. We can prove this again. I know that this is 2 times 2. But this exponent is telling me that there's not just one of these, but there's 2 groups of these. So here's my 2 groups. Well, 2 times 2 times 2 times 2 equals 2 to the 4th power. If I have q to the 3rd power, and I am raising it to, let's say, the negative 2nd power. All I'm doing is keeping my base, which is q, and I'm going to multiply 3 times negative 2, which gives us negative 6. So q to the 3rd power, all raised to the negative 2, is q to the negative 6. One last one. a to the 6, all raised to the 6th power. So what do we do? Well, our bases are a, and we're raising it a power to a power. So 6 times 6 equals 36. That one's done. Our next rule is what we call the power of a product rule. Okay? What's happening is when we have two numbers together, or two variables, and they're both being raised by a power. So let's do something easy here. Let's say we have 3a, and we're going to raise all of this to the 2nd power. This is kind of simple to like the distributive property. We're actually going to distribute this square a part of each individual coefficient and variable. All right, so what just happened here? All right, technically, what's the exponent of this 3? It's a 1. What's the exponent of this a? Technically, it's a 1. Okay, so since we're raising this, we're really going to say 3 times 1, that gives me 3 squared. All right, then we're going to square the a. That gives me a squared. Ultimately, we can figure this out to be 9a squared. All right, let's do a few more. All right, this is a combination of not just power of a product rule, but also power to a power rule. So I'm going to raise this r to the third power. Well, when I do that, it's really saying r to the 3rd times 3, based upon our previous rules. And then it's also telling me that it's going to be t to the 2nd power times 3. So ultimately, I get r to the 9th, t to the 6th. So r to the 3rd, t to the 2nd, all raised to the 3rd power gives me r to the 9, t to the 6th. Same principle. What is the exponent really for a? Well, technically it's a 1. We should know that any number raised to the 1 power is that number. Okay? So a to the 1st raised to the -2 is really saying 1 times -2. So we get a to the -2. b squared raised to the -2 power is b to the -4 power. c to the 3rd raised to the -2 is c to the -6. Now you might be wanting to try to combine all this, but remember, you can't. These bases are different. A cannot be combined with B. It cannot be combined with C. This is as simple as we can make it at this moment in time. The next one we're going to do is the power of a quotient rule. It's very similar to power of a product rule, in so much that you're just basically taking your terms and raising it to an exponent. So if we were to have something as simple as this, say a squared divided by b squared, and we're raising everything to the 2nd power. It's the same principle. I'm going to raise my numerator from a squared to the 2nd power, which we know to be 2 times 2, so we could write this as a to the 4th. Do the same thing with our denominator, b to the 2nd power raised to the 2nd power, which was 2 times 2, we know also to be b to the 4th. There's nothing else we could do with this currently. The bases, notice this, the bases are different, so I really cannot do any other exponent rules on this. This is as far as we can take this problem. So if I have 2, and I have 3, and I raised it to the -2 power. Well, we're going to do the same principle. What do we know is technically as the exponent of this 2? We know it to be 1. We also know 3 has an exponent of 1 because any number raised to the power of 1 is that same number. Now we're going to follow the same rule. We're simply just going to multiply. Well, 2 to the first raised to the negative 2 is 2 to the negative 2. How do we know that? Well, 1 times negative 2 is negative 2. 3 to the first raised to the negative 2 gives me 3 to the negative 2. Right? There is more we can do with this problem. Okay, there really is. There's a lot more. However, this is as far as I want to take it right now. When we start combining more of these processes, you'll see how everything will work together. The next one, it tends to confuse people because it seems to be really wordy, but it's not as bad as people make it out to be. All right, this is what you need to understand. If you ever take a number and you raise it to the negative n, you flip it and get rid of the negative. What do I mean? All right, so let's do an easy number. Let's go 2 to the negative 2 power. Well, technically, we want to flip this number. What do I mean by flip it? If this were a fraction, it would be this number all over 1. Okay, think back to fractions. If you have a whole number, it's always divided by 1. That's your denominator when you're working with whole numbers. So we have this. We want to flip it. Well, what we end up doing is the 1 becomes our numerator. Our base goes to our denominator. And the exponent, it stays a 2, but the negative gets dropped. All right? So really what we've just done is we've said that 2 to the negative 2 power is equal to 1 over 2 to the second power. We can also finish this out and say 1/4, because 2 to the second power is 4. Let's try some more. We have b to the negative 3rd, or negative 3rd power. All we want to do is flip it. Automatically, you should be thinking, hey, I need to put this number, b to the 3rd, under 1 and get rid of the negative. We don't like negatives. We get rid of negatives. And in order to do that is if it's on the top, we pull it down to the bottom. Right here, the negative is technically on the top. We put it on the bottom. AB to the negative 2. All right? This a square, it's positive. We like it. We like a square because it has a positive outlook on life. All right? So we're going to write it down. But we don't like b to the negative 2 power because it has a negative outlook on life. So in order for us to get rid of him, we're going to push him away. Since he was right here on the top of the world, we don't like him because of his negative attitude. We're going to push him to the bottom of the barrel. And we're going to make him happy whether he likes it or not by dropping his negative attitude. That's the way you can look at it. All right. So, those rules with negative exponents kind of bring us to this next piece. It's where it says rules for negative exponents and fractions. Again, seems wordy, but it's not so terribly bad. We can write things to make our life easier. When you see a negative exponent, it's what's happening, or a fraction being raised to a negative exponent. What it's really doing is telling you flip the denominator with the numerator. That's really what's happening here. So in this particular case, let's say we have 2/3 raised to the negative 2 power. Well, I don't like negatives, so I can automatically just do something really simple. I can get rid of this negative by saying, hey, all these, we're going to rewrite you, and we're going to say 3 over 2 to the second power. We've just made our life a little easier. There's another way that we could do this. I tend to use this way a little bit more often. is I know that this is going to be 2 to the negative 2 power, because this is technically a 1 here. 1 times negative 2 is negative 2. And I know that this is going to be 3 to the negative 2 power. All right? Well, just like before, I don't like negatives. And because I don't like negatives, if it's in the numerator, I'm going to put it in the denominator. And I'm going to drop its negative attitude. And if it's in the denominator, I'm going to push it up into the numerator and get rid of its negative attitude. So I can rewrite this. I don't like negative 2 to the negative 2 power. So I'm pushing it down. And I can say 2 to the 2nd power as my denominator. But I don't like this guy either. So I'm going to push him up and drop the negative attitude. I can rewrite this again. 3 squared is 9. 2 squared is 4. All right. The biggest thing I want you to really take is this major rule. We don't like negatives. Our idea is to get rid of negative exponents. That is the whole gist of everything. If it's in the denominator, you get rid of it by rearranging it and putting it in the numerator. If it's in the denominator, you rearrange it to put it in the numerator. That's the big take from this. We don't like negative exponents. So we've covered all the basic rules. However, I need to give you a warning. All right? This is not generally covered in math books. It's just kind of a given assumption that you know this. But this is what you need to understand. When you are taking a negative number and it's being raised to a power, the negative on that number is not raised unless it's in parentheses. Huh? All right, let me explain this. If I take negative a and I'm raising it to the 6th power, okay, the only thing that's being raised to the 6th power is the a, not the negative. Why do I mean that? Well, I've told you before, and you should know this already, technically what's in front of this a is the number 1. So this is saying negative 1 times a to the 6th power. So when you go to do this, it's just going to be negative a to the 6th power. However, let's change it. Same thing, except I have it in parentheses. This is following the power of a product rule. Excuse me, the power to a power rule. I'm sorry, I said it wrong. Okay? What's happening here? Well, technically there's that 1 in front of there. So this negative 1 is being raised to the 6th power. And this a is being also raised to the 6th power. Well, we can do some more with this, but I just want you to see that for now. All right, let's change it slightly. Let's say I was raising it to the 5th power. Well, the negative 1 is being raised to the 5th, and the a is being raised to the 5th. Okay? Again, there's more we can do to this, but I just want you to understand this one concept. All right, let's go through here. If I have negative 5 raised to the 0 power, this 0 is only raising the 5 and not the negative. We know that any number written to the 0 power is 1. So our answer for this is just going to be negative because it's not being affected. 1. However, if it was written like this, it means that everything inside that parentheses is being raised to the 0. So that negative is being raised to the 0. So it's technically a 1. The 5 becomes a 1. So the answer for this is 1. Notice the difference between the two. Don't believe me, put it in your calculator and you'll see what's going on. So here's what you need to do. If you ever raise a negative number to an exponent, make sure you put it in parentheses in your calculator because it's going to follow these same rules. One last one. I want you to notice something. If I take a negative, it doesn't matter what negative number, and I raise it to an even number, excluding 0, the answer is always going to come out positive. So if I have a negative a raised to an even number, whether it's 2, 4, 6, 8, 10, it's going to come out a to whatever power, to that even power. If I have a negative a and I raise it to an odd, it's going to come out negative a raised to whatever that odd power is. Okay, so remember, this is kind of in your notes. It says this: if a negative is raised by an even power, the answer will become positive. If it's raised by an odd exponent, it will become negative. Okay, so remember that word of caution. Be very careful on that. Your job now is, I'm going to give you about 4 problems. We're going to give you 2 at a time. I want you to pause the video and try to simplify each expression to the best of your ability. After you're done, unpause the video and see how you did. I do need to remind you something. I do need to tell you this. The way you solve it might be different than the way I solve it, because these rules you can mix and match as you see fit. Okay? But as long as we get the same answer, it's all gold. So remember that. Just because I do it a different way than you did doesn't necessarily mean that you were wrong. So pause the video and unpause it and see how you did. Alright, so in this first one we have 3t divided by t to the 4th. What we want to do is try to get all the things that are similar together. Well, first off, let's look at this 3. Well, is there anything that we can divide the 3 by? If you said no, you're wrong. Technically, like I've said, there's a 1 that's in front of this. We don't normally write it, but it's known. So we can say 3 divided by 1. Well, what's 3 divided by 1? 3. Yes, we could have just wrote 3 down, but I want you to understand why we write 3 down. Now let's look at it. We're going to do t divided by t to the 4th. This follows our quotient rule. What are we really doing? Well, technically this t is being raised to the 1 power. So we're saying t to the 1 minus 4. This could be written as 3t to the negative 3. If this is where you stopped, you would get this wrong. We're not completely done. Yes, this is correct, but it's not completely correct. Why? I told you we don't like negatives. And if a negative's on top, we're going to push them down. And if a negative's on bottom, we're going to push them up. That's what we do with negative exponents. We don't like their negative attitude. Well, what stays? Well, the 3 we're happy with. He has a positive outlook on life. But we don't like the negative 3. So we're going to push t to the negative 3 down. And when we do, he drops his attitude. So t to the 3rd. So 3t divided by t to the 4th is 3 divided by t to the 3rd. Now let's look at this next one. A couple ways we could do this, but let's keep it this way. I am going to raise each piece to the negative 2 power. Alright? So really 2 has what exponent? Has a 1. So 2 to the 1st being raised to the negative 2 is 2 to the negative 2 power. So far so good? Now we're going to raise this x to the negative 3 to the negative 2 power. Well, in order to do that, negative 3 times negative 2 is x to the 6. Now, if this is where you stopped at, partially right, but you still got it wrong. Why is it wrong? We don't like negative exponents. This 2 to the negative 2, we don't like him. So instead of him being where he's at, we're going to push him down. But the x to the 6, we do like. So he gets to stay right where he's at. So we push 2 to the negative 2 down, and he loses his negative outlook on life. And now it becomes 2 squared. If you got this far, you are still not done. You got one last step. X to the 6 stays just like it is. He's happy. But when we take 2 and raise it to the second power, we get 4. So 2x to the negative third, all raised to the negative 2 power, is x to the 6 divided by 4. Let's take a look at the next two problems. So here are your last two problems. They look tough, but if you take it easy and take it slow, you'll be all right. One thing I will caution you on is on number 3, just because this is 15 and this is 3, and technically their bases don't look the same, there is something you can do with it. I want to see if you can figure it out. There are something you can do with the 15 and the 3. You might be able to see it right now just by looking at it. And be cautious with number 4. It looks complicated, but again, take your time. So pause the video, try it, and we'll talk about it. All right, so number 3. What do we have going on here? We have 15n squared t to the 5th, all divided by 3 to the negative 1 t to the 6. Well, here's the cool part. I told you that there's something we can do with the 15 and the 3. Well, I've already said it. We're going to simply divide. 15 divided by 3 is 5. Okay? Just that simple. Now we're going to follow our rules. We have n squared divided by n to the 1, negative 1. So what we know we're going to do is we're really saying n squared minus the negative 1. Be very cautious. This is not minus 1, but minus negative 1. And now we could say t to the 5th minus 6. Let's rewrite this. 5n, well this is going to become n to the 3rd and t to the negative 1. If you got to this part, you're still not completely right. Why? Simply put, we don't like negatives. So we need to get rid of t to the negative 1. How do we do that? We push them away. So 5n to the 3rd divided by t. Why did I write t and not t to the 1st? Well, we know t to the 1 power is just t. Let's look at this next one. There's a couple of ways we could do this as well, but let's just keep it simple. Let's follow our rules. We're going to raise everything to the 32nd power. So n to the 32nd, r to the 32nd, and t to the negative 64. Woo. Divide by r to the negative 2 and t to the 32nd. That's what we've gotten so far. So if you got this, so far so good. All right. Now let's look at each individual piece. N to the 32nd. Is there anything here that on the denominator that we could do? No. So we're going to write it down. N to the 32nd. R to the 32nd. R to the negative 2. Since this is division, we're going to subtract. So we're really saying R to the 32 minus a negative 2. Again, caution, this is not minus 2, but minus negative 2. Now we're going to do t. T to the negative 64 minus 32. Let's finish this out. N to the 32nd. Well, R is going to be 32 plus 2 gives me 34. T to the negative, this is going to be 96. Wow. This is going to, all right. If you've gotten so far, so good. However, do we like negatives? No. So we're going to rewrite this finally, and I'm going to put it right here because I'm running out of board space. We're going to find out that it's n to the 32nd times r to the 34th divide by divide by t to the 96. Again, these numbers look hard, but if you do it one step at a time, following those procedures, you'll be fine. In scientific and technical work, we oftentimes find numbers that are really inconvenient for us to work with, such as what's behind me. We have the Earth's mass, which happens to be a number that I don't even know how to say. I could Google it, but I'm not. All right, and then look at the next one. Some X-rays have a wavelength of, here's another number. I don't even know how to say. I could look it up, but I'm not. These are both in what we call standard notation. This is how we would correctly write it in some ways. However, as you could probably guess, it took me a while to put a lot of zeros up on the board. Some calculators and some computers can handle this type of thing. However, most of the time, it's a whole lot easier just to write this in what we call scientific notation. And in order to do that, here are your rules. So what I want you to do at this moment in time is pause the video and write down this information in your notes, and when you're done, unpause it and we'll discuss it. When you have a number and we need to write it in scientific notation, we generally express it as what you see here, a number between 1 and 10 multiplied by 10 raised to the power of k. What did I just say? Basically, what we end up doing is taking the standard notation and moving the decimal in such a way that it's between 1 and 10, and then we multiply it by 10. Well, k, what that represents is how many times we move the decimal in order to make the new number p, and the k also tells us what direction. So your question, so what ends up happening is, let's cut back to classroom. The Earth has a mass of whatever this number is, and so when we actually use scientific notation, we end up getting 6.6 times 10 to the 21. That's a whole lot easier to say than whatever number this was. All right? And the same thing with this X-rays, where this would become 9.5 times 10 to the negative 8. Both of these things are easier for us to understand in scientific notation than it is for us to understand in standard notation. So the question that we have to ask ourselves is, how do we do this? So in order to go from standard to scientific, there's some rules that we need to follow. It should be right here. And basically it states this, that if you move a decimal to the left, your exponent will be positive, and if you move it to the right, your exponent will be negative. What do I mean? Well, let's look at this. I told you that we wanted to rearrange this number so that it's between 1 and 10. Well, how do we do that? Well, we go from left to right. We read from the left and we find the first non-zero. Well, the first non-zero happens to be this 1. Well, since it's there, what we automatically should do is put a decimal there. What we just did is we rewrote this number to become 1.5. Now, what we've got to figure out is the k part to our equation. All right, how do we do that? Well, one, we count how many times we moved the decimal. The decimal was originally here, but we moved it once, twice. So it's going to be 1.5 times 10 to the second power. The question that you need to ask yourself now, though, is this going to be a -2 or a +2? Well, look at what your rule says. It says that if you move the decimal to the right, it is a negative. Well, did I go to the right? Yes. So, when I write this number in scientific notation, I get 1.5 times 10 to the -2. All right, let's look at the next one. Same thing. We need to rewrite this in such a way that it's between 1 and 10. So, we start on the left side, find our first non-zero number, and it happens to be 1 again. Well, we put a decimal right there. So we have just changed this number to say 1.34, and now we're going to multiply it by 10, and now we got to figure out what k is. So how do we do it? Well, in this problem, where was my original decimal point? Well, it happens to be right here because it was a whole number. So, how many times did I move it? I moved it 1, 2, 3, 4. So 4 times. What direction did I move it? Well, I moved it to the left. And according to my rules, if I moved it to the left, it's going to be a positive number. So, 13,400 is 1.34 times 10 to the 4th. Alright, Now we're going to reverse the process. We're going to go from scientific back to standard notation. So our rules again are written right here, but pay attention, these rules are slightly different than the last one. And this time it says that if the k is positive, we're going to move our exponent to the right, and if it's negative, we're going to move it to the left. So let's do this. So the best way to start is write your first number down, 1.83. This is telling me I need to move my decimal 5 times. But since it's positive, our rule states that we're going to move it to the right, which is this direction. So we're going to go 1, 2, 3, 4, 5. And there's my new decimal place. And wherever there's a number missing, we just put a number in its place. So ultimately, what we find out is that this becomes 183,000. So 1.83 times 10 to the 5th is 183,000. All right, let's do the next one. Start off with your 4.8. It tells you you need to move it 3 times, and the negative tells you you need to move it to the left 3 times. So you go 1, 2, 3. Move your decimal. All right? Wherever there is an empty spot, you put a 0. So ultimately, you get 0.0048. Now, in most math classes, this would be an accepted answer. However, not in this class. You've got to do one more thing. You need a 0 here. There is a reason for it, and it has something to do with working in technical stuff, and I'll explain that in more detail in class. As you know, so this is a big pet peeve for me. If you come out with a decimal, always put a 0 in front of your decimal. Make sure that happens. I'm not going to spend a lot of time from going from standard notation to scientific notation and back. You should know this by now. However, I do need to give you a word of caution. First off, the rules that get you from standard to scientific are different than the rules that get you from scientific to standard. Make sure that you don't accidentally use one rule when you're supposed to be using the other rule. So be very cautious on that. And again, like everything I'm going to be telling you, read the problem and take your time. You're less likely to make mistakes. Alright, so what we want to do now is actually take scientific notation and help us in our daily calculations. The number that you see up here is a pretty massive number times another pretty massive number. And it's, yes, you could plug this into a computer, or you could look it up on the internet, or you could plug it into your calculator, and it's quite possible that you could find it, okay? However, sometimes it's just easier just to do it the old-fashioned way and do it by pen and paper. All right, so the first thing we need to look at is this first number. Well, let's write this in scientific notation. I know that based upon my rules, I'm going to have 1.11, excuse me. And I need to find out how many times I moved my decimal place. I moved it 1, 2, 3, 4, 5, 6, 7, 8, 9. I moved it 9 times. So this number written in scientific notation is 1.11 times 10 to the 9th. So let's do the same thing with the next one. This is going to give me 4 times 10 to the 1, 2, 3, 4, 5, 6. 10 to the 6. Okay? Now this is the easy part. We simply multiply. We multiply these two numbers first. 1.11 times 4. Why do we do that? Because they are our P. If we go back to the equation of scientific notation, they're the same thing, so we can multiply them. When we do, we get 4.44. Now, we need to multiply these two. The 10 to the 9th times 10 to the 6th. Go back to the rules of exponents. When you are multiplying, you simply add the exponents. Well, my base stays 10, and 9 plus 6 equals 15. Anywhere else in the world, this question would be 100% correct. However, since we're doing technical issues, we're always going to make sure that our answers are rounded to the correct precision or accuracy depending on the situation. Go back to the rule of significant digits. When you multiply numbers that are approximate, such as what we have here, these are not exact, we always round to the correct accuracy, which meaning in this case is we find the number with the least amount of significant digits. So let's look at it. Significant digits on this one, we have 1, 2, 3. And significant digits on this number, we have 1. So ultimately what we are going to do is round this number to one significant digit. Well, what we get is just 4, because that 4 tells that 4 to stay the same. The other numbers become zeros, they get dropped, and we get 4 times 10 to the 15th power. So in this problem we have 3.45 times 10 to the negative 6 times 4.2 times 10 to the 8th. Alright, so this one's already written in scientific notation for us, so we can just simply multiply. So we do like we did last time. We multiply our first two numbers, 3.45 times 4.2. So we have a handy dandy calculator that allows us to do that. 3.45 times 4.2, and I get 14.49 times 10. So, because that's my basis. So now we got to figure out what our exponent's going to be. Since I am multiplying, I'm going to take the negative 6 and I'm going to add to the positive 8. Negative 6 plus 8 gives me 2. Alright, so if this is where you want to stop, you would not be completely correct. So far, this is okay, except for one thing. Our rule states in scientific notation that this number that we have right here has to be between 1 and 10. Right now we have a 14. So we need to move the decimal place one more time. In order to do that, we move it this direction. And because we've moved it that direction, this number is going to increase. So we get 1.449 times 10 to the third. Alright, so in the normal world, this would be it. However, because we're doing technical stuff, we always do the correct rounding. Our accuracy states that we need to go to the least amount of significant digits. This has 1, 2, 3. This one has 2. So we're going to round to 1, 2 sig figs. This 4 tells that 4 to stay the same. These two numbers become zeros, and we drop them. So it's 1.4 times 10 to the third. In this problem, we have two scientific notations actually being divided. Previously, we've been multiplying, but the procedure doesn't change. We simply divide our p-values first, and then we follow the rules of exponents, just like we were doing with what we would normally do with division. So I'm going to divide my p-values. 8.03 divide by 2.1 using the handy-dandy calculator. So we get this number, 3.823809, blah, 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 blah. I'm not writing all that out. Times 10. So now we've got to figure out our exponents. This is negative 6 divided by the negative 9. Now remember, since we are dividing the exponents, since we're dividing them, we're actually going to subtract. So it's negative 6 minus a negative 9. Make sure you don't just say negative 6 minus 9. It's a negative 9. So what we end up doing is negative 6 minus negative 9 gives us positive 3. Now, because we're trying to make sure we get to the correct accuracy, we need to look at the number of sig figs. This has 1, 2, 3. This has 1, 2. So we're going to round our answer to 2 sig figs, which happens to be 1, 2. That means that this 2 tells that 8 to stay the same. In doing so, we get 3.8. All these other numbers become zeros. They get dropped. Times 10 to the third power. Alright, so here are 3 problems I want you to try on your own. So pause the video now and then unpause it and see how you did. Alright, so here are your answers. We have 1 is 8 times 10 to the 15th, 2 is 7.739 times 10 to the negative 2, 3 is 2.11 times 10 to the 11th. I'm not going to go over this in this video because I feel like you probably understand it already. However, if you are struggling, please come ask me and I'll talk to you one-on-one more about this. Oftentimes in mathematics, we are asked to find the principal root of a number. And the way this is noted is in this form, okay? Where the symbol, that little check mark with a line over it, is what we call the radical sign. The number that's under that radical sign is what we call the radicand. And then finally, this right up here is what we call our principal root, or most time we just call it root. Okay. So what is this really asking us to do? Really, when you get something like this, and it's easier to see it in a number, but it's really saying what number times itself n times gives you a. So let's explain that a little bit easier with actual numbers. So in this problem, what's being asked here is what number multiplied by itself 6 times is equal to 2. There are several ways we can do this, really just 2 ways. One, we can use a handy dandy calculator, which is what I'm going to do anyway. Or 2, we can do guess and check. Why do guess and check when we have the tools that we can do it? So if we were to plug this into the calculator, what we would end up finding is that the answer would be 2. All right? So we found out that the 6th root of 64 is 2. What does that mean? What it's telling us is this. If I take 2 and multiply it by itself 6 times, 1, 2, 3, 4, 5, 6, I'm going to get 64. So let's find out. 2 times 2 is 4. Times 2 again gives me 8. Times 2 again gives me 16. Times 2 again gives me 32. Times my last 2, and I get 64. That's what this is asking. What number times itself n times gives you a? All right. When dealing with principal roots, there are several different types. We can go 6th root, 18th root, whatever. However, there are 2 main roots that we'll constantly work with throughout our life. The first one that you know already is called square root, and we write it as such, where it's the radical sign with the number or the radicand underneath it. Notice how there's no principal root in here. There's no n there. However, in mathematics, we generally understand this to be the number 2, but we're just too lazy to write it, so we just write it like this. All right? There are several types of important square roots. We also know these to be called perfect squares. Again, you should know these by now, but in case you don't, here's a list of them. So these are the most common square roots that you find. Square root of 1 is 1, square root of 4 is 2, square root of 9 is 3, and all the way down. I'm not going to read them all. We also know these numbers to be called perfect squares. 4 is a perfect square because we know that 2 times 2 equals 4. Again, should be reviewed for you. If you do not know these by this time of your life, memorize them now. Okay? I don't ask you to do a lot of memorization in this class. I try not to if I can help it. However, these square roots, these perfect squares, they will be seen constantly throughout your life. And so these are the top 12 square roots, also known as your perfect squares, that you need to know. The next major principal root that we'll be working with is called cube root. Notice how in this particular one the principal root is 3, and so we're really asking is what number multiplied by itself 3 times gives us a. All right, and these are the most common. We know that if we multiply 1 by itself 3 times, we get 1. So the cube root of 1 is 3. And we can do this all the way down. Again, just like with square roots, I don't ask you to memorize things often. However, I do expect you to know these. I'm going to give you a word of caution. Sometimes when you are working with numbers, you may find out that you have a negative number under a radical sign. Such as this case, we're looking for the square root of negative 81. And in this case, we're actually going to be looking for the cube root of -8. All right. Now, you need to be very cautious in this because sometimes you may get some weird stuff. So, case in point, if we were to put this in our calculator right now, you'd probably get an error message. And it would say something like non-real or imaginary. Okay? But if you put this one in your calculator, you're going to get an answer, -2. Why is that? Well, here's the reason for it. Notice this. This is an odd root. Well, what's really right here? The number 2, and it's really an even root. You can never, ever, ever find the even root of a negative number. It doesn't exist. It's something what we call imaginary numbers. So in this particular case, I was trying to find the second root of -1. Because I was trying to find an even root, it doesn't exist. It's an imaginary number. However, since I was finding the odd root of -8 here, it does exist. Well, we can prove it. Well, -2 times -2 is 4. Times -2 again, I get -8. So that works. All right, so if I were to do anything, let's just change the numbers around. Okay? If I were to go to the sixth root of negative, and I'm making this up by the way, 1200, you're still going to get an error. It will not work because this is an even. You can never find the even root of a negative number. However, if I were to find this, let's say we're going to find the fifth root of -243. If we were to put this in our calculator, we would get an answer of -3. Why is that? Because it's an odd root. So, the big takeaway I need you to understand, you can never, ever, ever find the even root of a negative number. It will always be imaginary. But while you can always find the odd root of a negative number. Now, lastly, I will say this. We will be talking more about imaginary numbers later on in the semester, but not right now. So just kind of be able to identify them. All right? If it's an even, if you're finding the even root of a negative number, it will be imaginary. The last thing we're going to do in this video is simplifying square roots. And your instinct probably for this problem was just simply to plug it in your calculator and see what you get. And if that's your instinct, you would be wrong. That's not what simplification means. It's not just, okay, see what the number is. We need to make it easier to use for other mathematical processes. So for like this particular case, what we're going to try to actually do is factor out any perfect squares that we can divide 8 by. What do you mean? So perfect squares. Here are our list of perfect squares that we discussed earlier on. All right, so we need to go through them and find the largest perfect square that we can divide 8 by. Okay, and what we're going to do, that's what is called factoring. Okay, so perfect square number 1 is 1. Nope, won't work. Let's go to the next one. 4. Well, 4 can go into 8. All right, that works. 9. Can 9 go into 8? No. So the largest perfect square that can go evenly into 8 is 4. So we just found this out. We're going to write a radical sign. We're going to put the number 4, and we know that 4 times 2 equals 8. Okay? So we just kind of broke this apart between the highest perfect square that we can factor out, and then we got 2. We can rewrite this as the square root of 4 times the square root of 2. It's just one of those mathematical principles that we are able to do. Okay? Well, what's the square root of 4? Well, according to our rules, or to our list there, it's 2. Times the square root of 2 is 2. So we rewrite square root of 8 as 2 times the square root of 2. And you're done. You have simplified it. So now we have the square root of 75. So same principle applies. We need to look at our perfect squares and see what we can factor out. What's the highest perfect square? We have 1, 4, 9, 16, 25. 25 can go into 75 3 times. So we can say 25 times 3. We can rewrite this as the square root of 25 times the square root of 3. And we know that the square root of 25 is a perfect square, so we can say 5 times the square root of 3. Alright, now we have the square root of 82 plus 68. Your instinct might be to break it up individually and find the square root of 82 plus the square root of 68, but you can't do that. It won't work, mathematically speaking. The reason being, both of these are under the radical sign, and because it's an addition piece, we can't factor. Earlier, we were able to break things up by factoring out the perfect square was because they were multiplying. When we have that multiplication, we're allowed to factor. However, in this case, we can't currently factor because we have an addition. So in order for us to even work this problem all the way through, the best thing for us to do is to go ahead and add. So when we do, we find out that this is 150. All right? So we've just kind of changed the problem now. So now we want to simplify the square root of 150. Well, how do we do that? We go back to our perfect squares again. What's the largest perfect square we can divide 150 by? Well, again, in this particular case, the largest perfect square we can use is 25. So I can rewrite this as saying 25 times 6. Well, because I'm able to multiply under the radical, I can break this apart. And I can say that it's the square root of 25 times the square root of 6. Well, square root of 25 is 5, and we can't do anything with the square root of 6, so we write it down. So, the square root of 82 plus 68 is really the square root of, is really 5 times the square root of 6. Alright, last problem. Again, you might want to break this out and try to factor it, but you can't because we have to do everything under the radical sign first before we try to simplify. So we need to work with our exponents first. So we can really say that this is equal to 3 squared, which is 9. 9 squared is 81. So we have the square root of 9 plus 81. Well, we still can't really do anything with it until we add these two together. We get that to be the square root of 90. Well, now we can go ahead and start factoring. What can we factor out? Well, we need to look for our biggest perfect square. 1 won't work, 4 won't work, but 9 will. So I can factor this and say that this is 9 times 10. Or I can rewrite it and say the square root of 9 times the square root of 10. And I get 3 times the square root of 10. I want you to try these 3 on your own, so pause the video and unpause it to see how you did. Here are your answers. I'm not going to go over this for the sake of time, but this video is running long, and for that I am very sorry for. We're almost to the end, but if you do have any questions concerning these problems, don't hesitate to talk to me. That finishes this video. However, what I want you to make sure is to be prepared. Any of the questions that were presented or problems that were presented in this video may pop up as a little mini quiz on your next day of class. So be very careful of that. You'll probably see me pull maybe one, 2, or 3 questions from this video. So, and it's no surprises. Anything that's from this video is fair game, okay? Also, I need you to understand something. I've told you about this in class and I will tell you again in this video. If you did not understand something, you need to talk to me. I cannot help you if you don't ask. That is my pet peeve. Don't go whining that you don't understand something and say I never helped you if you never asked. So make sure if you need help, come talk to me and I will gladly help. Alright, see you in the next video.